Welcome to the lectures in chemistry on the topic of atomic structure and chemical bonding. My name is Mangala Sundar and I am a professor in the Department of Chemistry, Indian Institute of Technology, Madras, and my email coordinates are given here: mangal@iitm.ac.in and mangalasundark@gmail.com. So, this is a video tutorial. Problem solving is an extremely important exercise for any area in engineering and science, and more so in quantum mechanics. And so, we have already have some experience with the tutorials and the online submissions and so on, but these are some of the problems which require a bit of elaboration, and some of them are direct application of the formulae, the others additional concepts are provided and so on. Therefore, I request all of you who are listening to the quantum mechanics course for the first time to go through all these problems by yourself without having to necessarily do it with my help. Attempt these problems by yourselves, and then you come back to the video help in case you have some doubts. Okay. So, let me start with the problem sets. There are 10 problems in this tutorial, and the video tutorial has problems on 1 and 2 dimensional box problems based on the lectures which were made available to you. The first part contains about 6 problems of numerical as well as simple algebraic exercises in 1 dimensional model, and the remaining 4 problems are in the 2 dimensional box model. Okay. Some of the constants that I would like the students in chemistry and physics to have in memory. This is, these are fundamental constants, and it is important to have them in memory. The Planck's constant, as for example, as 6.626 times 10 to the minus 34 joule second, and then the other constants are also given here: speed of light in vacuum, the atomic mass unit, the mass of the electron, and the Boltzmann constant. These are constants which would be used throughout this exercise. The first problem is on the application of the model, the particle in a 1 dimensional box model, to understand the Heisenberg's uncertainty relation. So, it says that verify the Heisenberg's uncertainty relation for a particle in a 1 dimensional box using the lowest energy wave function. We will find out that the lowest energy wave function itself, the psi 1 of x, which is root 2 by L sin n pi x for the sin pi x by L, sin pi x by L, we can see that this itself will give you the result for the uncertainty in the measurement of position and the measurement of momentum uncertainties, the product of which would be greater than h bar by 2. We will see that, and this involves the calculation of the expectation values, and the first definition that you must remember or recall is the uncertainty in the position is given by this formula, that it is a square root of the difference between the average of the square and the square of the average, and delta p likewise is given by the square root of the average of the square of momentum and the square of the average of the momentum. Okay. And the average values are calculated in quantum mechanics, as you recall from the formula, that if you have the wave function psi, the average values are psi star of x in 1 dimension. For example, the operator A associated with the measured value A, psi of x dx over all space available to the system, assuming that these are normalized. to unity. So, psi star psi d tau is 1, okay, assuming that. So, we have to calculate the expectation values of the position first and the expectation value of the square of the position in order to calculate the delta x. I think this exercise of calculating the average value for x is something you already know. It is 2 by L, because the wave functions are root 2 by L sin pi x by L and the square. So, you have sin square pi x by L x dx. X does not operate on sin square sin pi x by L except to give you a product, and therefore, it does not matter whether you put the x between the two signs or the sin square and so on, and the box length is 0 to L. Okay. So, this integral is a standard, it is a fairly simple integral to do. It is 2 by L into 1 by 2, you express the sine square using the double angle formula, 0 to L 1 minus cos 2 pi x by L x dx, and the 2 goes away to give you 1 by L, and there are two integrals here between 0 to L x dx, and the other integral is between 0 to L x cos 2 pi x by L dx. Okay. This is well known, it is x square by 2, and between the limits 0 and L it gives you L square by 2. Okay. The second integral is 1 by L, we call it as I, and I is 1 by L 0 to L x cos 2 pi x by L dx. Okay. Now, calculate this integral using the u dv formula, process for solving the integral. So, we will write this I as 1 by L times 0 to L x d sin 2 pi x by L divided by 2 pi by L. Okay. So, that is the u dv formula, and that is, if you recall, integral u dv between the limits 0 to L is u v between the limits 0 to L and then the integral 0 to L v du. So, the same thing that you have to do here, which is 1 by L, which gives you this 1 by L 0 to L. It is not the integral, it is the limit. It is not the integral, it is the limit x sin 2 pi x by L divided by 2 pi L between the limits 0 and L, and then the other part of this integral is 1 by L integral 2 pi by L, sorry, L by 2 pi L by 2 pi sin 2 pi x by L dx between 0 and L. It is easy to see that this is 0 for x is equal to 0 and also for x is equal to L, because for x is equal to L it is a sin 2 pi which is 0, and this integral is 0 because it is an integral of a sine function over the entire cycle. For example, the sine function over the entire cycle between 0 and L. Therefore, the areas cancel each other, therefore, this integral is 0, this integral is 0, therefore, the average value of x is L by 2 since I is 0. Okay. This is easy. Therefore, the square of the average, which is one element for delta x, is L square by 4. Okay. Now, in exactly the same way you have to do the integral x square average, and it requires the evaluation of this integral 2 by L 0 to L x square sin square pi x by L dx, and again this can be written using the u dv formula. 2 by L into 1 by 2 x square into 1 minus cos 2 pi x by L dx, and this is sum of two integrals. So, it is 1 by L. The first one is 0 to L x squared dx, and the second integral is 0 to L 1 by L x square cos 2 pi x by L dx. Okay. Now, in the lecture notes that you find on the website, the details of calculating this are given. They are the same as the details for calculating the x, and you would see what the final answer is for this calculation. It will be L square by 3 minus L square by 2 pi square. Okay. Therefore, the delta x value that you want to calculate. So, let us highlight these two things. This is the average value x square, and the average value x square is L square by 4. Therefore, you see delta x is square root of L square by 3 minus L square by 2 pi square minus L square by 4, which gives you square root of L square by 12 minus L square by 2 pi square. Okay. Square root, this is the average value delta x. Okay. Yeah, I think we should technically use, but I have not been using the bracket, so let us leave it like that. Now, in a similar way, you want to calculate delta p, and for that you have to calculate the average value for p and the average value for p square. So, let us do that very quickly. The average value for p, now you have to be careful about placing the operator between the wave functions, as is the requirement in the calculation of the averages, namely it is 2 by L, the integral 0 to L, and its sine pi x by L, and the operator for p is minus I h bar d by dx, and the wave function on the right hand side is also sine pi x by L dx. This is important. In the case of position, you did not worry about putting the x in between, because it is anyway it is just a product, whereas the differential operator acts on the sign to give you something else, and therefore, you have to ensure that this is the precisely how the expectation values are defined by placing the operator between the two wave functions, and so you have to make sure that you do not miss that. Okay. Now, this is also easy to evaluate, because the answer is minus I h bar 2 by L pi by L integral 0 to L sine pi x by L cos pi x by L after taking the derivative dx, and this is the integral sine 2 pi x by L dx 1 by 2 between 0 to L, again over the full cycle. Okay. Therefore, p is the expectation value of p is 0. This is 0. Okay. Now, what is the expectation value of p square? It should be obvious from the way p square operator is used to get this wave function, but anyway, let us write that out. It is 2 by L 0 to L sine pi x by L minus h bar square d square by dx square acting on sine pi x by L dx. Okay. And this you know is essentially the same sine pi x by L you get, except with the minus pi square by L square. Therefore, what you get is plus, it is a 2 by L into minus h bar square into minus pi square by L square integral 0 to L sine square pi x by L dx. Okay. And 2 by L times all of this is the normalization of the wave function. The answer is 1. Okay. All of this is the normalized wave function property, and therefore, this gives you h square by 4 pi square h bar square into pi square by L square, which is h square by 4 L square. Therefore, delta p, which is given as the square root of the average of p square minus the p average square, is the square root of h square by 4 L square. Therefore, delta x delta p now becomes square root of L square by 12 minus L square by 2 pi square from the delta x, and this becomes h square by 4 L square. So, the L's cancel off and h square becomes h, and what you have inside the square root is h by 2 here, and inside the square root you have 1 by 12 minus 1 by 2 pi square. And you can show that this is greater than 1 by 2 pi, greater than 1 by 2 pi. Therefore, delta x delta p is equal to or is greater than h bar by 2 or h by 4 pi. The numerical value, if you calculate this turns out to be 0.181, and that is obviously greater than the h by 4 pi, and therefore, the uncertainty principle is verified. The uncertainty statement is verified. This is an important problem, and similar uncertainty statements have to be verified for every such model, namely the model for the harmonic oscillator, the model for the particle in a particle on a ring, the model for the hydrogen atom, and any other experiment. And uncertainty principle never fails in any of these models, and therefore, it is a fundamental principle. And the problem is chosen to tell you something about how to calculate the expectation values and how to take the averages, and then how to compute the differences and so on. Okay. So, this is an important problem. Now, the second problem, this is problem 2. So, the second problem gives you a different wave function. The wave function for a particle in a one dimensional box is given by this function psi of x is equal to c x times L minus x, where L is the length of the box and c is a constant. Therefore, it is asking you to calculate the average value, ignore these two x's, these are errors, calculate the average value for the energy, and the second is this an eigenfunction of the momentum or the Hamiltonian. Okay. The second one should be obvious that it is not an eigenfunction. So, that is the first thing we will do. Problem 2, minus h bar square by 2 m d square by dx square psi is equal to E psi is the equation that we solve. Now, if you are given the psi as c x into L minus x, where c is the normalization constant, does it give you this function back? It does not. In fact, what you get out of this is minus h bar square by 2 m, and there is only one minus x square term, and that gives you minus 2. So, it gives you h bar square by m. The function is not recovered, therefore, it is not an eigenfunction of the Hamiltonian. Likewise, if you think about the momentum operator acting on this function, the momentum is minus given by the operator minus I h bar d by dx, again acting on C x into L minus x, gives you the answer minus I h bar times C into L minus x if you differentiate the x, and if you differentiate L minus x you get a minus 1, then you get a minus C x. Therefore, the answer you get is minus I h bar C into L minus 2x. This is not the same as C x into L minus x. It is different. It is a different function. Therefore, this function that is given in this problem is not an eigenfunction of the momentum operator as well as the energy operator. Why do we have to worry about it? I mean, if you just ask the question, if an arbitrary function is given, why, if we do not know what the eigenfunctions of a Hamiltonian, why should we worry about arbitrary function? Because that is quantum mechanics. We never know, except for the elementary model problems, the exact eigenfunction of any problem. In fact, the search for the solution of the Schrodinger equation is the search for the exact eigenfunction. Therefore, what we do is to express the supposed eigenfunction in terms of some arbitrary functions with specific properties, and then we try to extract from that a relation to the eigenfunction. So, the fact that the function is given C x into L minus x as an arbitrary function is not entirely arbitrary, because it also satisfies the boundary condition that you require, namely phi of x is 0 at x is equal to 0, phi of x is 0 at x is equal to L. I think the boundary conditions cannot be violated by any of the arbitrary functions, because if they are violated, then they are not even solutions of that particular problem. So, it is important that when you see arbitrary basis functions or arbitrary wave functions, it is important to study their properties. First, verify that they satisfy all the boundary conditions for the solution. In this case, of course, it is 0, and therefore, it is an acceptable wave function, but it is not an eigenfunction. In the case of particle in a one dimensional box, we already know all the eigenfunctions, and they are given by the formula root 2 by L sin pi x by L sin 2 pi x by L root 2 by L, and likewise infinite number of eigenfunctions are already known. Therefore, why do we need to worry about the C x into L minus x? Because we do not know what is the state of a system until we measure it, and quantum mechanics tells you that when we measure it, the result is one of the eigenfunctions, and if the measurement is on the measurement of the energy, the result is one of the eigenvalues. Until we measure, we do not really know what is the state of the system is or what the energy is, and therefore, we can only calculate an average value for the particle, the energy, an average value for the particle position, the average being the average of many measurements, and the formula in quantum mechanics tells you that it is the average of infinitely large measurements given by that integral formula, namely the expectation value of A is the psi star integral A psi of x dx for one dimension. Okay. Therefore, quite a lot of these concepts in the very early stages they can be exemplified by simple problems, and it might take a while for you to get into it, but it is important to solve these problems. Okay. Now, the second part of this question, or the first part of this question, is evaluate C. If I remember, calculate the average value for the energy. Of course, we need to know what C is in order to do the energy calculation. Okay. So, there is one way of doing it, namely if you want to calculate the average without evaluating C, you can do it, namely you write to the wave function psi of x, and the energy operator is minus h bar square by 2 m d square by dx square for the particle in the one dimensional box, write psi of x dx between 0 to L. But since you know that the wave function is not normalized, you have to ensure that the wave function is written psi of x dx 0 to L. So, if we set this equal to 1, if not, the c square will cancel out and the lower integral needs to be calculated. So, let us do the following. Let us first evaluate c such that the integral psi of x square dx 0 to L is 1, okay. And in this case it is 0 to L c square x square into L minus x square dx is equal to 1. That is what we want for the wave function to be normalized. Therefore, it is easy to do this integral 0 to L. It is x square L square minus 2x L cube 2x cube L plus x raised to 4 dx. And between the limits 0 to L, the x square gives you the integral, gives you x cube by 3, and that gives you L cube by 3. So, we can write this straight away as L cube into 1 by 3 minus 1 by 2. This will give you x cube x 4 by 4, and therefore, it will be L 4 by 4 with a 2 it is 1 by 2, and the other will give you 1 by 5. So, the answer is, and will also be an L square in each of them. L square in each of them, because there is an L square here, there is this is L raised to 4 and this is L raised to 5. So, what you have is c square into L to the 5 by 30, that should be equal to 1, and therefore, c is root 30 by L raised to 5. So, once you know this normalization constant, then the energy average value, it has to be average because it is not an energy operator. This function is not an eigenfunction of the energy operator. And now you write 30 by L raised to 5 because of psi square, and then you write x into L minus x with the operator minus h bar minus h bar square, sorry, minus h bar square by 2 m d square by dx square on x into L minus x dx, and this gives you the answer minus 2, and therefore, you get plus. So, you get 30 by L raised to 5 into h square by 4 pi square into 1 by m, and then the integral between 0 and L x into L minus x dx. This is a very simple integral to do. It is x square by 2, so it is L cube by 2, and this is x cube by 3, and therefore, this is minus L cube by 3, and the answer is L cube by 6. And so, the final answer is 30 by L square h square by m into 4 pi square, there is also a 6. So, this is 5 by 4. So, the answer is 5 h square by 4 m L square pi square. Okay. And this is clearly greater than the lowest possible energy h square by 8 m L square. Later, when you study the atomic structure, you will realize that any arbitrary function will always give the they will give you the average value greater than the exact ground state eigenfunction. It is called variational theorem, and we will see that, but you can immediately notice that an arbitrary function gives you values which are greater than the lowest eigenvalue. Okay. So, there are quite a few things which are exemplified by solving this problem. Okay. Yeah. So, the next problem is to use the wave function in a slightly different way, the complex form. The particle in a one dimensional box, the differential equation is given by obviously d square psi by dx square plus k square psi is equal to 0, where k is given by the parameter the 2m times E by h bar square. Okay. M is the mass of the particle and E is its energy eigenvalue. The question is whether the following solution is also the right solution. Verify that the general solution is A exponential I k x plus B exponential minus I k x, where A and B are arbitrary constants. Are the conclusions of the lecture still valid for the solution? So, the wave function is psi of x is equal to A e to the I k x plus B e to the minus I k x, and the differential equation that we want to do check with is d square psi by dx square plus k square psi. What does it give you? Okay. So, the first is to take the derivative d by dx of A e to the I k x plus B e to the minus I k x. The derivative gives you I k times A e to the I k x minus B e to the minus I k x, and the second derivative d square by dx square on psi is one more derivative on this I k d by dx on this whole function again. The answer is I k whole square. A e to the I k x again, but now the sign of B will change, it becomes B e to the minus I k x. And now you see that this is nothing but psi of x. Therefore, I k square is obviously minus k square. So, the differential equation that we have is d square psi by dx square, and that is equal to minus k square times psi. So, that is the same thing as that. Therefore, this wave function gives you the answer that it satisfies the differential equation d square psi by dx square plus k square psi is 0. Okay. So, no problem, it is also an eigenfunction. And that should be obvious, because when you write A e to the I k x using trigonometric forms, it is cos k x plus I sin k x psi of x is equal to plus B cos k x minus I sin k x. Okay. We want to find out whether the conclusions of the previous lecture using the cosine and sines, are they valid using these functions. Okay. So, let us go back to the form and see if that is true. So, what you have is this is cos k x times A plus B plus I sin k x times A minus B. Now, the conclusion is that psi of x should be 0 at x is equal to 0, which implies that when x is 0, cos k x is 1. Therefore, this gives you A plus B, and this is 0. Therefore, A plus B is 0, or A is equal to minus B. Okay. When you substitute this into your equation psi of x, when A is minus B, you are getting psi of x is equal to minus 2 I b sin k x, because this term will go to 0 when A is equal to minus b. So, you have that. The only thing we have is minus 2 I b instead of b in the lecture, but remember, when you normalize the wave function psi of x square into dx is equal to 1 between 0 to L, this integral, the 2 is irrelevant, it will get cancelled out, and the I, now please remember this is true for the real functions, whereas the normalization integral in general for complex function is psi star of x psi of x dx between 0 to L. Therefore, if we have the wave function psi of x is minus 2 I b, then psi star will be plus 2 I b and the psi will be minus 2 I b, and then the rest of it will be sine square k x, and you will see that the complex number goes away and b will be such that this whole thing will give you exactly the same result, namely root 2 by L sine k x. So, all the conclusions that we have by using the exponential formula are reproduced, and they are no different from the functions, the trigonometric functions, because they are anyway linear combinations of the trigonometric functions. Two things are important. One, no matter what constant you put in, when you say h psi is equal to E psi, if psi is multiplied by a constant c, then h on c psi is E on c psi, and therefore, the equation is still valid. So, psi is defined only with respect to a numerical constant. The second thing is h psi, if psi is multiplied by a complex number e to the I delta, okay, and if you multiply on the right hand side also by e to the I delta psi. Okay. This is no different, because when you write the psi star psi dx for normalization, the complex number will go away, e to the minus I delta, e to the I delta times all the other things, this I. Okay. Therefore, the wave function is defined to within an arbitrary constant to be the same, and the wave function is also defined with respect to an arbitrary phase. The complex phase factor is irrelevant for the wave function overall. The purpose of bringing in this problem is to highlight these two conclusions, namely the arbitrary constant and the arbitrary phase factor. Okay. Let us go to the next problem. Problem 4 is an algebraic calculation for you. The momentum operator associated with the position coordinate x in one dimension is given by the form p is equal to minus I h bar d by dx, and therefore, you are asked to calculate the commutators. Commutators are important, and commutator essentially, I think it has been defined in the lecture. If not, let me do that now. Let us go to problem 4. You have seen this in matrices in the mathematics earlier. The commutator of two operators A and B is AB minus BA. Okay. These are operators, therefore, sometimes I use the hats and sometimes I do not, but remember that in the context. Therefore, if you are asked to calculate the commutator x and p, it is the commutator of x and minus I h bar d by dx. Okay. To evaluate this, it is easier for us to calculate this for an arbitrary function phi of x, and then see how phi of x is, the results are the same independent of what phi of x is. So, let us do that. Therefore, it is x into minus I h bar d phi by dx, that is a b, and then minus b a is minus I h bar d by dx on a phi. Now, the operator d by dx acts on both a and phi, and a is also a function of x. Okay. And in this case, what? So, the derivative here is minus I h bar x d phi by dx plus I h bar d by dx on x is 1 and therefore, you have I h bar phi, and then the other thing is that d by dx operating on the phi, which gives you plus I h bar x d phi by dx. Okay. And these two cancel out, and so the answer is I h bar phi. Now, phi is an arbitrary function for the commutator x p acting on, and the commutator x p acting on that function is therefore equivalent to multiplying that function by I h bar. Therefore, the commutator equivalence is x comma p is equivalent to I h bar. Usually, some textbooks write the unit operator in order to say that this is the left hand side is an operator and therefore, the right hand side should also be an operator. But remember the context. The context is should be multiplied by I h bar and a unit operator. Okay. So, given this, the remaining commutators in the problem that you have, is the commutator x comma p square, x square comma p and x square comma p square to be calculated. Let me do that very quickly also. And these are illustrative of the algebraic methods which are important in quantum mechanics. Let us go to x comma p square. So, x comma p square, if you recall the derivative, the definition of the commutator, it is x p p minus p p x. So, let me keep this x p in mind, because we know the answer x p minus p x is I h bar. Therefore, we can write x p is equal to I h bar plus p x. So, to solve that, what we can do is to write x p p minus p x p, and let us add p x p again and do minus p p x. Okay. Now, imagine, look at this, and this is x p minus p x on p, and look at this, this is p on the left hand side, x p minus p x. Therefore, you know the answer, this is I h bar p, and you know the answer, this is I h bar p. So, the answer is 2 I h bar p. Okay. In fact, if you have an operator a, b, c, it is easy to remember the mnemonic that this operator commutator is given by the left goes to the left, the right goes to the right, and whatever remains as a commutator. So, if the left goes to the left, it is b and the commutator is a c, and if the right goes to the right, the leftover is the commutator a b and c is on the right side. This is the mnemonic. This is how the rule should be remembered for operator commutations. Is exactly the same thing. You can easily verify that if you have a b on the left hand side as a commutator, as an operator with the c commutator, again the left goes to the left, the right goes to the right, you will get the answer. It is a times b comma c plus a comma c times b. Therefore, the operator x comma p square we have already done as 2 I h bar p. What about x square comma p? Again, that is easy, it is x comma p. So, if you recall our rule of left and right, the left is x with an x comma p, and the right is also x comma p with an x, and what you have is I h bar x plus I h bar x, because the commutator is I h bar times a number unit operator. Unit operator of course commutes with, then the number goes away, number commutes with all these operators. So, you have 2 I h bar x. Now, I would leave it to you to show using the similar form that x square comma p square is 2 I h bar x p plus p x. exactly the same way. Okay. So, this is to give you some handle on operator manipulations, which are important, because in fact very often many physicists believe that quantum mechanics is also stated in one line as the commutator between x and p being equal to h bar. That is a fundamental statement that was first identified by Werner Heisenberg and Max Born, and in fact the tombstone of Max Born is supposed to have this inscribed in the cemetery where Max Born is buried. It is a fundamental statement. So, commutators will become important as you go as you read more and more in quantum mechanics. Let us go to problem 5. Yeah. The next problem is a simple application of the one dimensional particle in a box to linear molecular systems. This is a standard example that you find in many books on how to approximate the electronic states and also the transition between the different electronic states using the particle in a box for the specific case. So, the problem reads like this: the one dimensional linear chain of conjugated hydrocarbon system can be approximated usefully as a box for electrons in. This is the conjugated system, CH double bond CH, single bond CH, double bond CH, and so on. If there are n double bonds, then you can see that the chain has a certain length. And since there is the bond length is average bond length for CC, the box length may be calculated, and you can see that leaving the edges out, there are 2n minus 1 bond lengths. The electrons are quite free to move, and to a first approximation we neglect the interaction between the electrons. So, this is a statement. What is the problem? With that as a background, now you calculate the energy difference between the highest occupied energy level and the lowest unoccupied energy level in the ground state of one such conjugated system 1357 octatetraene using this model. Now, in order to do this, of course, there are other requirements, namely in each energy level of the particle in a box model that the electrons are supposed to be part of, no more than 2 electrons can occupy an energy level. Recall the Pauli principle that no 2 electrons will have all the quantum numbers identical. So, keep that in mind, that in any given energy level there are only 2 electrons, and that the electrons also do not interact with each other. Therefore, the potential inside the box is 0. Using the bond length of the CC 1.33 angstroms, calculate the delta E between the highest n up to which the electrons are there and the lowest n in which there is no electron. There are 4 bonds. The box length is about 7 CC bonds average. Therefore, the one dimensional box length is 7 into 1.33 angstroms. So, that gives you 9.31 angstroms, or 9.31 into 10 raised to minus 10 meters in SI units. So, this is the L, and the m is the mass of the electron, single electron. Even though there are 8 electrons, they do not interact with each other. Therefore, there are no other effective masses. Each electron behaves independently. So, the system is a particle in a one dimensional box with n electrons, but each electron is by itself. Therefore, the m is the mass of the electron. So, it is easy to calculate this quantity, the energy n, in terms of h square by 8 m e, mass of the electron, L square, n square. H is known, m e is known, L is now known, and therefore, this number you can calculate as a function of n square. Okay. So, the answer turns out to be, when you do these calculations, ensure that you put the units carefully, so that you do not make mistakes in algebra, in numerical calculations. So, if you write the En, h square is 6.627 into 10 raised to minus 34 joule second whole square into n square divided by 8 into 9.109 into 10 raised to minus 31 kilograms for the mass of the electron, and then multiplied by 9.31 into 10 raised to minus 10 meter square. So, you can see that the joule second will give you kilogram meter square per second will give you that per second, and then the units will give you joules when you cancel the units. Okay. The numbers are fairly straightforward to calculate. I would not do this, the actual calculation of these numbers. I think from what I have done, the answer turns out to be 6.95 into 10 raised to minus 20 joules into n square. If you think it is verified, it's okay. If it is wrong, let me know, so that I will correct that. But this is the number I have. This is n squared. Now, there are 8 electrons conjugated. Each double bond has 2 electrons which are mobile, and therefore, the 8 electrons will occupy n equal to 1, n equal to 2, n equal to 3, and n equal to 4 quantum states. Therefore, the delta E is the highest, the difference between the energy of the lowest unoccupied level, which is n equal to 5 squared, minus the highest occupied level 4 squared times h squared by 8 m l square. This you already know, and this is nothing but 25 minus 16. So, this is about 9 times h squared by 8 m l square. So, it is a fairly simple problem, but this is important to give an approximate estimate of the energy of transition for the electronic states in a linear system, and likewise you can calculate it for other systems using elementary models. Okay. Let us go to the next problem. Problem 6 is the calculation of the quantum number for the energy of carbon dioxide molecule in a 1D box of length LENGTH, there is a spelling mistake, but anyway 1 centimeter at 300 Kelvin. Assume it is potential free, that is, the carbon dioxide moves in a box which is potential free, and carbon dioxide's translational energy is 3 by 2 kBT, where kB is the Boltzmann constant. So, one has to calculate the n given the energy E, and one also notices that as the energy increases, the relative energy differences between the energies delta E by E, they go to 0, and therefore, the molecule behaves classically as E becomes very large. Okay. Now, the important point for this lecture, for this problem, is that the length is given as 1 centimeter. This is a macroscopic dimension, and for macroscopic dimensions, quantum conditions are not really important. And you would see that the quantum number corresponding to this value of energy 3 by 2 kBT for the electron in a box of 1 centimeter is ridiculously high, the quantum number. Therefore, you would see that it is not a quantum state, it is almost like a classical state. Let us see quickly what that is all about. Okay. So, when you say that the energy E is 3 by 2 kBT and T is 300 Kelvin and kB is 1.38 times 10 to the minus 23 joules. So, you know what kBT is, and 1.5, it is 1.5 times 300 into 1.38 into 10 raised to minus 23 joules. This is the E, and this E is given by h square by 8 m l square n square, and that is the kBT, 3 by 2 kBT. Therefore, to evaluate the n, let us do what is called the order of magnitude. I do not want to do exact computation, but I will simply give you the orders. Okay. H is of the order of 10 to the minus 34 joule second. So, H, that is a 6 point something, let us not worry about it, the square, and L is of the order of a centimeter. So, it is 10 raised to minus 2 meters, and the mass of the electron is approximately 10 to the minus 30 kilograms. Okay. Is 9 point something, 9.1 into 10 to the minus 31, which is 10 to the minus 30 kilograms. Okay. Therefore, if you want to calculate n square, it will be 8 m L square by h square into 3 by 2 kBT. So, kBT we have approximately 10 to the minus 21, 1 into 3 into 1.5. So, we can put it approximately as 10 to the minus 20, okay. And the mass is 10 raised to minus 30, and the L square is 10 raised to minus 4, and the H square is 10 raised to minus 68, 6 into 6, 10, 3 points, so it is 10 raised to minus 67. Okay. Now, if you look at this number, this is minus 34 minus 20, and this is n square. Let me see if the numbers are right. M is 10 to the minus 30, L is 10 to the minus, L square is 10 to the minus 4, H is 10, H square is that. So, into 10 raised to minus 20. So, the order is 34, 20, 54 and 10 to the minus 67. So, this is 10 raised to 13. Therefore, n is a square root of 10 raised to 13 of the order of 10 raised to 7, is a ridiculously large number. But the point to be made is that for a macroscopic dimension, for a thermal energy which is like 300 Kelvin, which is very high a temperature for a molecular system, you see that the quantum numbers are ridiculously very, very large, and therefore, quantum mechanics is not very relevant for macroscopic systems. That was the whole purpose of this exercise. The second thing that you have to do is, remember, when E n is given as h square by 8 m L square times the n square, E n plus 1, which is the next level, is obviously h square by 8 m L square into n plus 1 whole square. Therefore, delta E n plus 1 minus comma n, I would say, delta E is between these two levels, divided by E n. If you calculate, you see the answer is h square by 8 m L square into n plus 1 whole square minus n square gives you 2 n plus 1, okay, divided by h square by 8 m L square n square. So, this goes away. So, what you have is essentially E n plus 1 minus E n divided by E n is 2 n plus 1 by n square. As n goes to infinity, this goes as 1 by n plus 1 by n square, and therefore, it goes to 0. Therefore, delta E by E goes to 0 for very large values of E, which means that the energy levels are too dense and they are so continuous that the quantum description of energy discretization is no longer relevant. That was again the purpose for giving this problem, to see what is the classical limit or what is the correspondence, what is called the Bohr's correspondence limit, namely the masses are very large, the energies are very high, or the box dimension is the macroscopic dimensional boxes. All these things give rise to classical results. Next problem, please, which is now for a particle in a two-dimensional box. I mean, it's a 2 and 3 dimensions, but I think I'm only having some examples of two-dimensional problems. Okay. So, here it's a very simple algebraic exercise to calculate the particle's probability. So, consider a particle in a square box of side L. determine the probability of finding the particle in the area enclosed by x is equal to L by 3 to 2 L by 3 here, and likewise y is equal to L by 3 to 2 L by 3. So, this is the highlighted area. What is the probability of finding the particle in that area? It is just a simple formula which you have to remember. Psi x of y for any arbitrary quantum number n1, n2. You remember particle in a two dimensional box has two quantum numbers. This is given by the formula 2 by L sin n1 pi x by L sin n2 pi y by L. Therefore, psi square dx dy between the limits L by 3 to 2 L by 3, L by 3 to 2 L by 3 is what we are asked to calculate, and that is given as 4 by L square between the limits L by 3 to 2 L by 3 dx sin square n1 pi x by L times the integral L by 3 to 2 L by 3 limits dy sin square n2 pi y by L. So, these are the two integrals that give you the probability of finding the particle between x is equal to L by 3 to 2 L by 3, y is equal to L by 3 to 2 L by 3. Okay. This integral is fairly simple for you to evaluate, and therefore, I am not going to write the answer, but will just write the next step, namely it is 4 by L square integral L by 3 to 2 L by 3 dx into 1 by 2 1 minus cos 2 n1 pi x by L times the corresponding integral for the y, integral between the limits L by 3 and 2 L by 3 dy 1 by 2 1 minus cos 2 n2 pi y by L. Okay. This is easy to evaluate, and I will not worry about giving you the final results. Okay. You can calculate them. The next problem is on understanding the degeneracy. Consider a particle in a square box of psi dl. Determine the expression for the energy of the particle. It is a textbook, it is there in the lecture. If the total energy of the particle is 65 h square by 8 ml square, I mean this number was chosen to illustrate the degeneracy. Determine the degeneracy and write down the wave functions for all the states with the energy. Okay. Now, the first one is the expression for the energy of a particle in a two dimensional box, and that all of you who have gone through the lecture know that it is h square by 8 m L square. For a square box, it is n1 square plus n2 square. Okay. Now, the sum total is given as 65, and you can see the rest of it is the unit for the energy h square 8 ml square, and so you have n1 square plus n2 square giving you 65. So, find n1 and n2. What are all the choices that you have? Obviously, n1 is equal to 7, n2 is equal to 4 is one possible choice, and then the degeneracy implies that n1 is equal to 4 and n2 is equal to 7 is also the degenerate state, but these are not the only two states. Here n1 is equal to 8 and n2 is equal to 1 will also give you 8 square plus 1 65. Here it is 7 square plus 4 square, which is 65, and likewise n1 is equal to 1, n2 is equal to 8. So, there are 4 degenerate states. Now, what will come to you as a surprise, and you will see that in the future when you do more quantum mechanics, is that when there are degenerate states psi 1, psi 2, psi 3, for example, here psi 4, there are 4 degenerate states. Not only that these have all the same energy, but any linear combination of these 4 states A1 psi 1 plus A2 psi 2 plus A3 psi 3 plus A4 psi 4, any linear combination where A1, A2, A3, A4 are constants, they can be real or complex numbers. Okay. Any such state is also an eigenfunction. Therefore, when you talk about degeneracy, the linear combination of degenerate states themselves are eigenfunctions of the Hamiltonian if the states are eigenfunctions of the Hamiltonian, and there are infinite combinations, but linearly independent number of eigenstates for degenerate systems will be the same as the number of degenerate states. So, in this case there are 4. So, you may choose infinitely many choices for A1, A2, A3 and A4, but only 4 out of them will be linearly independent of each other. Everything else can be expressed as a linear combination of these 4. So, the dimensionality of the degenerate states is given by the simple exercise that you see. Okay. And writing these states is fairly straightforward for you. Namely, I will write this for one state, psi 8 1 x comma y is in our notation, it is 2 by L sine 8 pi x by L sine pi y by L. Quite obviously, the other psi 7 4 x comma y is written as 2 by L sine 7 pi x by L and sine 4 pi y by L, and there are 2 more states for each one of them with the 8 and 1 interchanged and 7 and 4 interchanged. So, these are the 4 states that you have. I think that is what this problem is asking you to do if the determine the degeneracy and write down all the wave functions. Okay. Next problem is a problem of a rectangular box with sides L1 and L2, and the question is to find out the expression for the energy of the particle. And for a specific ratio L1 is equal to 4 L2, what is the lowest energy state which is degenerate, and what is the degeneracy? Write down the wave functions for all the states with the energy. Again, I shall indicate the solution, not write down the solution verbatim. If you need it, I will always do that in a piece of paper and put it up on the website, but understand what it means. A square box is one in which L1 is equal to L2 and everything else is rectangular or any other shape that you have. So, if you have these, picture should be, if this is L1, this is 1, 2, 3, about maybe just about this, that is L2. L1 is 4 L2, therefore, this is L1 and this is L2. L1 and L2. Now, you can call it x or y. What is important is the wave function psi n1, n2 is going to be, for the one dimension it is root 2 by L1 sine n1 pi x by L1, and for the second dimension, if you recall, these were 2 one dimensional problems. Therefore, the second dimension, the normalization is 2 by L2 square root sine n2 pi y by L2. In the case of a square box, since L1 and L2 were the same, the root 2 by L and root 2 by L became 2 by L, and the expressions were very simple. But this is the rectangular box, and therefore, correspondingly the energy E n1 n2 is the sum of the 2 one dimensional energies, which is h square by 8 m L1 square n1 square. This is the energy in the dimension of L1, and the other energy is h square by 8 m L2 square n2 square. Okay. Therefore, to write this in common form, it is 8 m n1 square by L1 square plus n2 square by L2 square. This is the expression for the energy when you have a rectangular box. The n1 and L1 go together, n2 and L2 go together, when these two are equal, we had the simpler expression. So, this is what you have to remember. Everything else is finding out the corresponding numbers of L1 and L2. If L1 is 4, L2, what it means is the following. We have the energy for the particle in a box given by h square by 8m n1 square by L1 square. It is 4 L2. So, it is 16 L2 square, and the other one is n2 square by L2 square. Now, you have to find degeneracy for n1 and n2. I will give you a simple solution. If n1 is equal to, let me see, if n1 is 4 and n2 is 1, what do we have? We get h square by 8m 1 plus 1, 2. Okay. Does not do anything. Now, if n1 is 4 and n2 is 2, E is given by 4 is 4 square is 16, 1 and 2 square is 4. This gives you 5 h square by 8m L2 square. This is L2. Okay. And the other possibility for which you have the same energy is n1 is 8 and n2 is 1. You can calculate this as h square by 8m. If it is 16, it is of course 64 by 16. So, it is 4 by L2 square, and the other one is 1 by L2 square. So, you also get 5 h square by 8m L2 square. Okay. So, these two states, n1 is equal to 4 and n2 is equal to 2, and n1 is equal to 8 and n2 is equal to 1. These are degenerate states. Now, verify whether this is the lowest degeneracy or not. I will leave it to you as the problem. The last problem that we have for this video tutorial is the model similar to the particle in a one dimensional box for the linear chain. Now, we have a square box, and the square box is ideally modeled with cyclobutadiene as an example. I mean, these are approximate models and is used often as an example for a square box. And cyclobutadiene has 4 electrons which are relatively freer than the others, and assuming that they do not interact. I mean, these approximations are, you have to take them with a little bit of care. These are to illustrate what is meant by a model. So, if the 4 electrons are assumed to be non-interacting and are bound to the molecule tight, you can calculate energy difference between, again, the highest occupied energy state and the lowest unoccupied energy state. It is a square box and you are given the bond length. Therefore, you can calculate the sides of the square, that is the length of the box. So, let us see the answer. E n1 n2 is h squared by 8m L square. For a square box, this is problem 10. n1 square plus n2 square. You can write E11 here, E12, E21 here, and E22. The energy is now in the standard increasing progression. So, you can put 2 electrons in this, and you have 2 1 electrons in each of these levels. And so, what is the transition that is happening is one of the electrons going up to 2 2. So, the delta E that you are calculating is between 1 2 or 2 1, which is 5 h square by 8 ml square. Okay. That is a lower energy, so it is a minus sign, and the higher energy is 2 2, which is 8 h square by 8 ml square. L is given as 1.3, what is the number? I believe 1.4. So, this is given as 1.4 L. So, you can calculate into 10 raised to minus 10 meters, okay, and h is known. and mass is the mass of the electron, and therefore the energy difference between the highest occupied state and the lowest unoccupied state is 3 h square by 8 ml square. Okay. Now, this is the first of the few video tutorials I would like to have for solving problems which are slightly longer than a simple one dimensional quiz with multiple choices. Okay. Therefore, what is important for the listener is to tell me if such video tutorials are useful, and if you would like me to prepare more of them. I mean, obviously I cannot prepare many more, but at least about 5 or 6 such tutorials for the entire course, or even more, maybe even up to 10 tutorials, because we have a 12-week course. It's possible for me to prepare, but your input and feedback is important for me to continue this process for supporting the lecture materials with problem solving skills and enabling you to look into more and more detailed problems. I hope you will enjoy such tutorials in the future. Until we make the second tutorial or until we meet next time with the lectures, thank you very much.